in example 2, let's evaluate the definite integral, the integral from negative 2 to 1 of 2x dx. So we know that this is going to be equal to the limit as n approaches infinity of the sum from I equals 1 to n of f of ci delta xi. Here, the reason why we would know that this definite integral is going to exist is if we look at the function 2x, that's a polynomial. Polynomials are continuous everywhere, so in particular, it'll certainly be continuous on the interval negative 2 to 1, which means that this function will be integrable. So let's work on finding our delta xi. And for this example, let's just use fixed constant bounds. It usually tends to be the easiest case when you're able to do so. What we're going to do is we're going to chop this interval up into n equal parts. The width of the interval, so it's going to be b minus a divided by n. Whenever you use equal subintervals, that is, it's going to be 1 minus negative 2 divided by n, which is going to be 3 over n. So for us, delta xi is going to be 3 over n. I then now need to choose a selection point, ci, within each interval. And for us, for this example, let's just suppose we're going to use the right endpoints. The value of the right endpoints is going to be given by, so the interval starts at negative 2, and because the width is delta xi, which is 3 over n, I'm simply adding an additional 3 over n times I to go from one subinterval to the next. So this is going to be our ci, and now I know my selection point. I'm going to plug it into the function f of ci. Remember, f of x is 2x. So this is going to be 2 times negative 2 plus 3 over n I. F of ci is negative 4 plus 6 over n I. And I think I wrote this parenthesis a little bit too early. There we go. That looks better. So we have our delta xi. We have our f of ci. Let's go ahead and plug that into our Riemann sum formula. This is going to be equal to the limit as n approaches infinity of the sum from I equals 1 to n. F of ci, we said, was negative 4 plus 6 over n I times delta xi, which is 3 over n. This is equal to the limit as n approaches infinity of the sum from I equals 1 to n of negative 12 over n plus 18 over n squared I. This is equal to the limit. We can split this up into two sums. The limit as n approaches infinity. We have the sum from I equals 1 to n of this thing here, which is just a constant with respect to I. So we're going to get negative 12 over n, the sum from I equals 1 to n of essentially just 1, plus, again, with respect to the index of summation I, this is a constant. So it's going to be 18 over n squared times the sum from I equals 1 to n of I. We can now use our formulas. This is going to be the limit as n approaches infinity of negative 12 over n. The sum from I equals 1 to n of a constant is just that constant times n. So it's going to be times n plus 18 over n squared. The summation from I equals 1 to n of I, we had a formula for that. That was going to be n times n plus 1, all divided by 2. We can now go ahead and simplify this. This is equal to the limit as n approaches infinity. These cancel, so we get negative 12 plus, I can take the 2 into the 18 to give 9. And then what I'm going to do is we have this term here, which is what, n squared plus n. That whole thing's divided by n squared, so I can break it apart. And then this is going to be 1 plus 1 over n. As n goes towards infinity, we have constant, constant, constant. This thing will approach 0. And so what we're left with is in the limit, we get the following. This is going to be negative 12 plus 9 times 1 plus 0, which is negative 12 plus 9, which is negative 3. So the value given by this definite integral would be equal to negative 3. One of the comments or observations we make is because the definite integral in the previous example is negative, it does not represent the area of the region shown in the figure above. Definite integrals can be positive, negative, or 0. For a definite integral to be interpreted as area, the function f must be continuous and non-negative on the closed interval a to b, as stated in the next theorem. If you want to try to get some sense of what was happening here, if we sketch this function, so the function 2x is just a basic line graph. It has a y-intercept of 0 and a slope of 2. At negative 2, when we begin our interval, this would be down at a height of negative 4. At positive 1, it would be at a height of positive 2. And what we would see is if you're trying to think of the concept, not physically, but as like a negative area, if we look at kind of like the total area from left to right, there's more of the region that would be below the x-axis than what would actually be above the x-axis. And because of that, that's why the final answer for this definite integral ended up being a negative value. Okay. To summarize, this is summarized in Theorem 5.5. The definite integral as the area of a region. If f is continuous and non-negative on the closed interval a to b, then the area of the region bounded by the graph of f, the x-axis, and the vertical lines x equals a and x equals to b is given by the definite integral from a to b of f of x dx. So we need for the function to be non-negative, in other words, 0 or greater, to lie above the x-axis in order for that definite integral to have the interpretation of area.